Alrighty, welcome to part 3 of this video, in which we have some shapes on the screen we've drawn to a canvas, and what we're going to do is we're going to start wrapping up our draw function into a standalone function. And what I mean by that is we're going to take it out of the onload stuff and give it its own block that we can then call easily from somewhere else. So when it's all, say, function draw everything, you'll notice that when I type that, it looks a lot like fillrect and fill style in that I start with a lowercase word and then I have a capitalized word. It's called camel casing. It's kind of a traditional programming naming convention because you can't have spaces and names for programming. And anyway, you'll see that kind of thing all the time, but draw everything, because we're defining that function, unlike window onload, which is built in. Because we're defining it, we can name this anything. We could call this, elephant season. We could call it, bird flight. Doesn't matter. Anything you want to call it. It just should be descriptive of what's going on in there. And what we're going to do with it is draw everything. So let's call it draw everything. I selected this code that does our drawing, the black, the white, and the red rectangles. I'm going to cut it with Control X. You can right click and use that functional menu too. And I'll paste it between these open and close braces for draw everything. In that section right there in the middle. And the way a function works, at least in the simplest form like this, is that it just allows us to use this as a label to call it from anywhere else in our code. So this does exactly what we did before, in that when it gets to this label, it'll run the code inside here. Top to bottom, first brace down to the closing brace. I saved it, Control S or File Save in the menu. No change yet in the browser when I refresh. Let's say I put that down 3 different times in the text. But if I run this, it's going to look the same, right? Because it's going to draw the exact same thing every time. There's no change happening here. But I could prove it's running 3 times by using this console log. Remember how that works? I'm going to cut that with Control X, move my cursor down, zoom back in. I'll paste it around here and I'll say, instead of hello world, called draw everything. And we could spell it, we could spell it out nicely. We might maybe just want to use our actual name from the function. And now every time that this console log gets reached, we'll see it again printed out into our console log in the browser. So there we are, we've got it. I'm going to save it. It should see it 3 different times. And when I refresh in the browser, I see right there called draw everything all 3 times from line 18 of the code, because I'm calling the function by its label 3 different times. But what's going to be happening is, each time that we draw things, we're going to be moving them a little bit. So as long as we keep adjusting the position of something, it's going to appear to move along the screen. It's like how any animation would be drawn on paper too. So, just an example of doing that, let's say that each time we draw everything, we want to move where the ball is. Well, first of all, right now, every time we do this red thing, which that'll become our ball, is being drawn centered on the screen. How could we make it so that its position would change every time we draw it? Well, this is where we're going to see a much more normal use of var, or variable. So even though when you saw this canvas and canvas context a little confusing because we don't have anything like it, you'll be seeing a lot of this sort of thing. I'll say var ball x. Ball x should mean the horizontal position or the x-axis coordinate of a ball. This label could be anything. Just like I said, draw everything could be, elephant season. This could just say, wings, or this could say sewers. Any word. It's just a label for legibility to us. That's a clue to us of how we're going to use the number or other value that it stores. I'm going to initialize or set this number up to be 50. And what that means is that this label now refers to 50 in the computer's memory. And instead of drawing the ball, this red rectangle, at a position canvas width divided by 2, I'll draw it at position that's stored in ball X, which we set up here to be 50. I can save this, zoom back out. When I refresh it, I'll see there's my red rectangle, which again, that'll become our ball. It's being drawn at position ball X, but it's not yet changing. Well, okay, we can change it. Inside draw everything, each time we update the screen, let's increase the value in ball X. Now, if you're new to programming, the way we're going to do this is going to look a little bit weird, so let me explain what's going on. We're going to write ball X equals ball X plus 10. Now, if you're coming to this from a math background or anything else, this looks broken. Like this expression, this equation can never be correct, right? Like it's not, you can't make something equal to itself plus 10. The important thing to know about programming is that a single equal sign has nothing to do with a balanced equation like it does in algebra and programming. In programming, what it does is it takes the value on the right side and it saves it into the label on the left side. It just copies it over, it overwrites it onto the left. So if I said here, draw everything equals 70, that would store the number 70 into this label, and then the ball would be drawn at position 70 instead of position 50. If I told it to set itself to ball X plus 70, then on the right side it's going to evaluate. It's going to see, okay, what's stored in ball X? At first, the number 50. Then it's going to add 70 to it, so 130. Is that right? 7, 8, 9, 10, 11, 12, 120. Which means it's going to have 120 on the right side, save it into that value, and then it'll start drawing it there. And the next time it comes around to draw everything, the second time it calls it, it'll add another 70 up to 190 and so on. Let's stick to smaller numbers that I can handle adding. With a 10, the first time we call draw everything, it'll draw it at 50, or so it'll get here. It'll say it was 50, it'll add 10, it'll draw it at 60, and so on. You know what? All this is kind of hard to keep track of in my head. What if the computer did it for us? Instead of saying call to draw everything, right here, let's say, in this console log, just the name ball X. And what this is going to do is each time draw everything gets called, it'll print out what the value currently stored in ball X is. So we'll be able to see in the sidebar of our browser how that number is affected. I'll refresh it, and I'll see over here it was 60, 70, 80. Because each time I call draw everything, it was adding 10 more to the initial 50. Notice too that it's doing that before it prints out. So that's why we never see the 50. But that's a good place to put it because that's also, by the time that number has changed, is also when it's going to get used for drawing the rectangle. Now, if you watch it again, we don't actually see this rectangle move. We could even increase this number. And we'll save it. And I'll refresh. All right, I mean, these numbers are bigger. They're not growing by 20 instead of 10, so it's ending up further. But the problem is this is all happening so fast. The computer is calling these three functions at lightning speed. A computer, a modern machine, does just billions of calculations per second. It is way, way, way too fast, these number changes, for your human eyes to follow it. It's in fact too fast for your modern monitor to even display those changes quickly enough. So it's not like your eyes aren't good enough. It's like the computer doesn't even have time to update the screen. This code is happening so fast. So we want to slow it down in order to see those changes. And the way that we can do that, and this is a pretty important magic step in understanding how gameplay and game programming works, so follow along carefully here, this is a big deal, is we're going to set up a timer that's going to call draw everything at a regular interval. Now first we're going to do it at a crude, like once a second, but we can make that faster and make smoother gameplay. And the way that that's done in JavaScript, every programming language has this kind of own way of doing it, is we're going to say set interval, I'm doing this right here in window on load, draw everything, that's the name of our function, and then 1000. This is how many milliseconds I want to wait between each time the function gets called. I'm going to delete those times where I called it myself. Okay, so now right here, what I see is window on load. It waits till remember the whole page is loaded, so that means draw everything has already been defined for the computer before any of this happens. It then sets up its canvas and canvas context, which we need for drawing our graphics. Then every 1 second after the page is loaded, it's going to call the draw everything function. Each time it does, it's going to add 20 to the value stored in ball X, which started at 50, and then it's going to display that number to the console, and it's going to redraw everything, the black rectangle, the white rectangle, and the red rectangle, but the red rectangle's position will be increased by 20 every second that we look at it. Okay, I'm going to save this file, Control S, or File, Save in the menu. Let's zoom back out, and when I refresh it, we have motion. And again, right there in the console over here, you can see this number is getting 20 larger every frame. And the position we're seeing for this red rectangle is the same as if we had typed in 330 or 350 or 370 or 390 for the horizontal position of our fill rect for what again will become our ball. Is that making sense? There's a lot going on here. And this doesn't just have to be a position. So even though I'm using it here, to mean the horizontal position of the ball, that's why I called it ball X, I could also say, always draw it 75 pixels from the left, but let's make the width of the rectangle connected to that ball X variable. So remember, all we have here is just a number that's in memory, starts at 50, increases by 20 once a second, and I can plug the number in here to change the width of the rectangle every frame, or every second, instead of the position. Let's see how that looks. And once again, this is identical to as if I had typed in 190, 210, 230, 250, 270, and so on. Each second it's updating and drawing, the next number where ball X has been increased by 20. Well, let's do one more crazy thing, all right? We can use that same label multiple places. We can have it also increase the horizontal position. We can have it also increase the vertical position. We can have it also used as the height. Now, this is a terrible programming practice. This is not something you would normally do in a program because this label means something to us as human readers, right? Ball X should mean the horizontal position or the x-axis coordinate of a ball. But here I'm using it in the positions that refer to, for the fill rect, the horizontal position, the vertical position, the width of the rectangle, and the height of the rectangle. Let's just look at what it does. Because what I want to show you is that the computer doesn't actually care about where these numbers are being put. It's as though I had typed in 250 or 270 or 290 to all four of those positions. This is just a label in the code for a number or a value that then we can do anything we want with. We can put it in those places even if it doesn't make legible, readable sense to us. It's printing out the number here that's exactly the same as if we typed in the number there once a second. Now, before we lose too much more control of what the heck's going on, let's sort of back out some of these weird changes. Let's keep ball X in a spot that makes sense as the ball's horizontal position. Let's also just put the ball 100 pixels from the top. Let's make it 10 by 10. That's closer to the shape of a ball, I'd say. Okay, save that with Control S, refresh in the browser. And now we're back to a normal thing of seeing this red ball moving along. Probably paid attention to the fact that when I press refresh, it's blank for a second. Why is it blank for a second? Because it's not calling draw everything until the set intervals happened the first time a full second later. For that matter, that's the reason why it's acting so choppy. We could make this number smaller than 1,000 milliseconds, or 1 second. Like, let's say we made it 500 milliseconds, or half of a second. If I save the program, we should see the ball move twice as quickly. It looks like about twice as quickly. I mean, the computer's a better judge of that than I am. Okay, well, what if we change that from 500 to 100, or a tenth of a second? Okay, now we're getting somewhere. That looks much, much faster. We can make this number even smaller. We can make it 50, and just zoom off the right side of the screen, right? We could decrease this number smaller than 20, the amount that's increasing it by every time, to like 5. And what we're going to begin seeing is something closer and closer to approximating smooth motion. And again, what you're seeing over here is every 50 milliseconds, it's printing out the new value for where the ball is. And how can we mentally test this? How can we check with ourselves that it's doing what we really think it is? Okay, remember, we set up our canvas, right, here in the code to be 800 pixels wide. That means that right when the ball is approaching the right side, we should expect to see that ball X, as printed out to the console, is around or reaching the number 800. Let's see if that's true. Okay, we've got a full screen view here. Refresh. Now watch the number over here. As the ball approaches the right side, we should see this getting nearer and nearer to 800, 600, 700, and 800 right there, right as it crossed the right side. Does it make sense now what's going on with these positions, these numbers? Hope it is, and if it's not, keep playing with it. It's going to become more and more natural as we progress.